Okay, so in the previous two videos about Frégier phenomena, we were looking at the envelope of chords, the spin chords, that are defined as two rays, these two blue arrows here. They intersect the ellipse at this point and that point, defining the spin chord, and then we were rotating this pair with a fixed angle in between, rigidly, and that so defined chord swept an ellipse. If I move them on surface on the boundary of the ellipse, I would get a different kind of ellipse. Okay? And what we did notice in the previous exercise was that over M, the area of these ellipses was invariant. Okay? Now let's look at something we did not talk about last time. What happens if the ellipse is a circle? So let's reduce A over B of the ellipse to 1. Okay? What happens if my ellipse has two equal semi-axes, therefore it is a circle? What happens to that envelope? That envelope becomes a circle. Okay? So if I have a point M, and let's go ahead and make this guy be 60 degrees apart, exactly 60 degrees apart, or perhaps 45 degrees so we don't have this kind of a symmetry, or perhaps let's go to 70 degrees. So here's 70 degrees, okay? What happens to the envelope of these chords when you have these two blue rays, these two blue arrows here, apart from each other by 70 degrees as I rotate the pair? In this specific case, I sweep a circle. Okay, so my Frégier envelope is a circle. Okay, of course I can place this anywhere, and I can change the rigid angle between these two blue arrows to a different value, and I'm going to get a different radius circle. In the limit, when the angle is exactly 90, so let's approach that. I'm at 98 now. Let's go to 95, 92, 93. As I hit 90, I get the Frégier point, and all I have is a family of right triangles. And as we know, that chord is going to have to be a diameter, and all these diameters are going to meet, or they're going to have the center of the circle in common. If I go down to 80 degrees, I go back to a non-Frégier, say ellipse kind of envelope, except that on this case, when A over B is equal to 1, I get a circle for that envelope. Okay, all right, so now let's switch gears. That's the subject of this particular video. I want to now marry this concept with the concept of Poncelet families. So here's a 5 periodic in the elliptic billiard. Now here's a vertex P1. So let's first of all watch this 5 periodic. You can see that this 5 periodic is inscribed in an outer ellipse and circumscribed about a confocal caustic, this brown thing here. Now let's define this particular vertex without loss of generality as P1. Okay, and I want to consider this angle here right now, this angle. So there's these two blue incident edges into P1, and there's an angle here. Now imagine I were to keep these two rays here, and I would consider this particular ray and that particular ray, and I would connect that and consider the chord that connects these two locations here. And I could do the same thing as we were doing before with Frégier. I could vary these two guys here, preserving their angle, but rotate them rigidly above P1, and consider the envelope of those chords, much the same way we did it before, right? So let's go ahead and draw the envelope. For P1, okay, this is the Frégier envelope. This is not a 90-degree angle, but this is the Frégier ellipse or envelope associated with this pair of blue directions here, if I were to rotate them about P1 while keeping their angle fixed. So I would get this envelope that you see here. Just like before, we have an ellipse. So as I move my periodic family, I animate that. And let's animate that slowly so we can watch what's happening. It should be animating, right? For some reason it is not, so I'm going to do it by hand. So let's see, why is it not animating? . These are not animating. There's a bug. Okay, that's okay. I'm going to stop it. I'm just going to do it by hand. So what happens when I animate the 5 periodic family in the elliptic billiard? In this situation here, you can see that the angle at P1 is almost 90 degrees. So my Frégier envelope is shrinking to a point. I don't control that directly, but it is the case that this 5 periodic is going to go through something close to 90 degrees. It's probably not exactly 90 degrees because that's not shrinking to an exact point, but it could be close in this position here. Okay, so that angle there is close to 90 degrees. But what we get is we get a family of Frégier envelopes. And what I'm showing up here, I was looking for invariants. You can tell that the axes of this envelope nor the ratio or product of these axes is constant. Okay, so there's nothing here. That's too bad, but I wasn't expecting much. Now the other thing I can do here is I can show for each of the vertices, I can show its associated Frégier envelope as built before, right? So you take each one of these vertices, you look at the two incident edges, and you freeze the angle in between them, and then you sweep a rotation around that point while keeping that angle. Okay, so now I have a set of, in this case, 5 objects, and I can watch what they're doing, and I can also perhaps look at the sum of those areas to see if they are invariant. They're not. So you can see here they're not invariant, and then we could try many different things, the product and other kinds of things, but I have found that none of these are invariant. Okay, so this is the set of Frégier envelopes for the elliptic billiard. What if we switch the family and we now go to the homothetic pair? Homothetic pair is interscribed between two homothetic ellipses. Here's the n equals 5 case, right? It's a different family. This family has constant area, and it has also constant sum of side length squared. But this is not germane to this conversation, so let's go ahead and look at one of the Frégier envelopes to this family. This one is with respect to point P1. And now let's go ahead and draw all of them. So here they are. I'm drawing all of them. Let's check if the sum of their areas is constant. It doesn't look like it is. Nothing really smart or really interesting about this. Okay. Now let's go to another Poncelet family called the in-circle family. And that's a family that has a circular caustic, this brown circle here, and it's inscribed in an ellipse. So here's a 5 periodic family interscribed between an ellipse and a circle, concentric circle. Let's go ahead and draw one of the Frégier conics of this family. So you can see here that it does shrink to, it's with respect to this vertex here. So when this vertex, the angle here is close to 90 degrees, the envelope shrinks to something that is close to a point, and so forth and so on. I'm not detecting any invariance looking at whatever I'm reporting, the semi-axis reported above. Let's draw the 5 Frégier envelopes. Again, nothing really smart going on here. I suppose I could change a little bit the aspect ratio, but there's nothing really remarkable going on here. I'll show you guys in the end what the locus of the C points are for each one of the families. There's nothing really interesting there either. Okay, so now let's go to the surprise. Okay, now recall what we were talking about before. Okay, the Frégier envelope when with respect to a point on a circle. Okay, I have a point on a circle here. My Frégier envelope is a concentric circle if my point is on a circle, and if my angle, of course, is not 90 degrees, because at the 90 degree situation I get the center of the circle itself, right? So just recall that. But when my angle is a little bit off from 90 degrees, for example 80, I get a concentric circle, or if I go to 95, I also get a concentric circle. Okay, if I go to 110, the circle becomes bigger, right, as I sweep this. So now let's consider another Poncelet family that has a circle involved. Okay, so that's the last one, and let's look at it first. It's the one with a circumcircle. Now let's look at this family. This family is interscribed between an outer circle and an inner concentric elliptic caustic. Okay, so let's just look at it. There it is. This is a family of 5 periodics interscribed between these two shapes. What are conservations? This family conserves the product of its cosines, and there's a few other invariants I didn't mention in the first one. The previous one, the in-circle family, this one conserves sum of cosines, as does the confocal billiard family, right? This family here conserves perimeter and the sum of cosines, and it is closely related to the in-circle family, which also conserves sum of cosines. Okay. Now let's go to the circumcircle one. Okay. So what's happening here? If I look at P1, P1 is inscribed, so the whole family is inscribed in a circle, but P1 is currently on a circle. So if I shoot a ray from P1 and another ray from P1, and I record that angle, so I shoot them along these two directions, and I record that angle. Okay, imagine a chord that is connecting these two vertices here. Okay, the envelope of that chord over all positions of this blue pair about P1, as I rotate this blue pair about P1, is going to be a circle. So let's draw that circle. There it is. So this is the Frégier envelope, or the envelope of the Frégier chords with respect to P1. Now it's a circle because I am on a circle. Okay? If I change the radius of the circle, I change my Poncelet family. Okay, but it does not, I'm not changing the radius of the circle, I'm actually changing the aspect ratio of the inner ellipse, but you know, from a scale neutral perspective, this is equivalent to changing the radius of the outer circle. But what I'm trying to say here is the following. If we don't change the fact that P1 is inscribed in a circle, the envelope of chords defined by the rotation of these two blue rays, rigid rotation of these two blue rays, i.e. preserving the angle in between, about P1, is going to be a circle. Okay? Now here's the one invariant that we did detect. Perhaps it's obvious, okay? Let's draw all of them. So now, if I consider all the vertices, each one of them is going to be associated with a different circle, because how can we explain this? The angle at each one of these vertices is different, right? So the radius of this circle, of this associated circle, is actually associated with that fixed angle, okay, what we called beta before. Okay, so if you see here, if I change my beta, okay, sorry, correcting myself, the angle between the two chords, between the two outgoing arrows, I'm calling it alpha. So if I change that angle, the radius of the envelope circle, or circular envelope, changes in accordance to alpha. Okay, so what's happening in this n-periodic situation, in fact, let's just look at this guy here as I rotate the family. You can see that the radius of the circle changes because the angle of the incident rays onto P1 is changing as well. So this is never becoming quite 90 degrees, because if it were becoming 90 degrees, that circle would shrink to a point. Let's change A over B to see if we can do that. So if I do that, no, this is closer to a circle, so let's go in this direction. Let's see if I can do that. Yeah, it doesn't quite look like I can reach 90 degrees. This could be a feature of this particular family that I'm never able to get to a right angle. Okay? Okay, so that circle never shrinks. But let's go back to something more reasonable. Something like, you know, A over B, internal, I don't know what that is. I'm not reporting that there, but I have an ellipse here in the middle. Okay. All right, so what is the result? The result is the following. Let's draw the 5 envelopes. There's 5 vertices. Each one of them has an angle. I'm going to associate with that vertex and that angle a circular envelope. Well, the beautiful thing is the sum of the areas of these 5 envelopes is invariant. Even though they're changing radius, you can see that I'm reporting the sum there with 6 decimal spots, decimal digits, and the sum of the areas is not changing. So that's the invariant that I found with this construction. It's probably not that exciting, but I couldn't think of a direct way to prove that. So if I go, for example, to n equals 4, n equals 4 is interesting because the n equals 4 family here is a rectangle. So these four angles are 90 degrees. Therefore, my four circles, my four circular envelopes are going to be points, and the sum of their areas is 0. But let's go to n equals 3. So here's a triangle, triangular family. And the interesting thing here is that these circles have to be tangent to each of the sides of the triangle. Look at this one. This one is tangent here, this one is tangent there, and this one is tangent here. The reason is that with the three periodic case, the chord itself is the opposite side. Okay, so the envelope needs to be tangent to the chord, and it's going to be tangent to the chord at this particular position, precisely at this particular position. So if I shoot this ray, I intersect my circle here. I shoot this other ray, I intersect my circle here. I have one chord, okay? And then when I move this pair here around P1, keeping its angle fixed, I'm going to sweep the circle, but the instantaneous envelope is precisely this tangency point. So this is verified for the three circles. This guy is tangent to this one, and this one is tangent to that one. So dynamically, the circles, or their changing radius, they're dynamically tangent to the three sides, okay? Okay, but notice that the sum of their areas is invariant. So there's a beginning step here to the proof. Can we prove that for n equals 3 in this particular system, the sum of the areas of the three circles is invariant? Okay, let's look at n equals 4. We saw that it's a rectangle. N equals 5. We saw that you get this more complicated picture, and the sum is also invariant. I suspect this is not going to be easy to prove. And then let's go for n equals 6. And you can see here also that the sum is invariant, and now there's something really cool happening. Since there's symmetry on these on this particular n, right? N equals 6 has the following kind of symmetry. This vertex is diametrically opposite to this other vertex, so they're both going to sweep the exact same circle, the exact same circular envelope. Likewise for this pair and this pair. Notice that this angle here is equal to this angle, okay? And that's basically enough for you to be guaranteed to sweep the same circle, even if the vertices were not opposite to each other. So this vertex and this vertex basically produce the same envelope. I don't know which one of the three is. That's the reason why you only see three envelopes here, okay, as we move around. You only see three distinct envelopes. Notice again that the sum of their areas is constant. Let's go to n equals 7. Now you're going to see 7 distinct envelopes, and the sum is also preserved. So this is this apparently is a phenomenon. Okay. All right, guys. Let me know if you have any cool strategies to prove this phenomenon. Thank you.